All right, so today we're going to have a quick, brief lesson on a topic called the Intermediate Value Theorem. This is used a lot in math. It's used for proofs, okay, but, I know you may have trauma from that word. We're not doing proofs like we did in geometry, okay? You don't have to worry about that. But it's more of just what's the word I'm looking for? Confirmation of things, okay? So the formal definition of intermediate value theorem is we have two values, a and b. They are real numbers, and a is less than b. Okay, so here I marked it out. A is over here on the left, b is over there on the right. Okay. If f is some polynomial function, okay, so right now, again, we're just talking about polynomials, all right, and this only applies to polynomial functions because like we saw earlier this week, right, polynomials are continuous, okay, and they're smooth, right? So there's no jumps, there's no tricky maneuvers happening, right? Very straightforward. And if f of a doesn't equal f of b, so when you plug those values into the polynomial, you don't get the same value, then the intermediate value theorem tells us that in between a and b, the function will take on every value between f of a and f of b. So I'm going to kind of plot this out. So say you plug in a and you get some point there. Okay, we're going to call that f of a, right? So that's where they meet. You plug in a, you get that y value f of a. You plug in some value b, maybe it's up there, and up here we have f of b. Okay, so here this is our interval, a to b. Okay, it's a closed interval. So, I mean, that's going back. So remember, that means we have equal here, right? Closed dots. So they're saying as long as we have a polynomial, then from a to b, we are going to cover everything in between f of a to f of b. Okay, so it may look, a little funky, but here I cover every value in between those two, that y interval, okay, from here to here. More specifically, this says that, how do I want to say this? If there's some value d, so if d is in the interval between f and a and f and b, then there has to be a value c such that when you plug it in, you get d. Okay, so here, it might be here. And there we have f of c equals d. Okay, so this is a lot of mathematical words, right? It may be a little confusing, but really what this is saying is as long as you have a polynomial, a continuous curved line, if you have 2 points, okay, then everything in those points has to be covered. Okay, so how do we use this in math? I mean, sometimes they use it, they use actually intermediate value theorem in a lot of things. But the one thing in math we use it for, okay, is to prove that a polynomial function has a real zero on a given interval. So what I mean by that is if we have some function right? So so again, we're just talking about, conceptually with a and b. So if we have a function f where f of a is positive and f of b is negative, then there must be, oh, I just misspelled where. Then there must be a value c where it is a solution, right? So it could be anywhere. Okay, but it must cross that x-axis. Right? So, sometimes you're asked just to prove that a function has a real zero. Right? So I'm going to show, we'll do one example together like that. So I'll give you a minute if you're finishing copying anything here. Just want to make sure I'm not missing anything. No. Is everybody good? Can I move on? Or does somebody need more time? I will take your silence as confirmation. All right, so let's look at one example. Okay, so we're going to use the intermediate value theorem to prove that there is a real zero for the function f of x equals x cubed minus x squared plus 1. Now notice, I'm not asking you what is that zero, right? I don't want you to solve this. I just want to be able to convey the message that there is a zero. Okay, so because remember, we saw there might not be a real zero if we have some function that never crosses the x-axis. Okay, so in a case where we have a parabola that doesn't cross the x-axis, we don't have any real zeros. We don't have any real number solutions. Now, I'll start off by saying, because this is an x to the third, and we know the end behavior of an x to the third rises to the right and falls to the left, well, just by common sense, it's going to have to cross at some point. Okay, but we don't know. That's what I'm trying to prove. Okay, so what we can do is make a table. So we're going to pick a couple x's. All right, so let's do -2, -1, 0, +1. All right, so we're going to plug these in. I'll do the work for you. We plug in -2, we get -11. We plug in -1, we get -1. We plug in 0, we get +1. We plug in 1, we get also 1. Okay, so we're looking for an area, an interval, where we change, like we saw before, okay, from a positive value to a negative value, or a negative value to a positive value. Okay, so right here we can see our y values change from negative to positive. So we can say by the intermediate value theorem, f of x must have a solution or 0 or x-intercept, however we want to say it. Okay, so by the intermediate value theorem, f of x must have a solution on the interval of your x values from -1 to 0. Right, and you're using a theorem as your proof. Okay, so that's really all you have to say if they're asking that for you. Okay, so all you're looking for is a spot where it crosses, right? So even if I just plotted out just this part, okay, at -1, I have -1. At 0, I have +1. So somewhere I have to cross that x-axis. And so once you have that, then you can take further steps to find the 0 if they ask it for you. Okay, one way to do it is to decrease our interval, right? So maybe I'm going to test from, I don't know, -0.7 to -0.3, right? I would plug those values in. If they're both positive or they're both negative, I know my 0 somewhere else. If I have one positive and one negative, then I know my 0 has to fall in between. I would try a smaller interval that fits that. Okay, so it's a process of elimination thing. But luckily, we have the tools, all right, or we're in the middle of learning the tools on how to find those zeros. All right, for this one in particular, okay, we actually have a 0 at x value of approximately. Okay, if you see this, it means approximately, so it's really close to, but it's not exactly equal to -0.775. Okay, so we won't be necessarily using this exactly, right? Excuse me. In terms of doing it like this, there may be like 1 or 2 questions in the future. I don't remember anything on this on the final last year, but this year we also have a midterm. Apparently, they're going to do. We'll see how that goes. But it is a good theorem to know about. Okay, and actually can help you out in real life. It's kind of logic, right? Unfortunately, logic is a topic that they used to talk about in geometry that they don't really anymore. It fits hand in hand with computer science. Maybe if we have some time at the end of the year, we'll talk about it. All right, any questions about the intermediate value theorem?